This will be given by Luigi Vanfretti, who is an associate professor at the Rensselaer Polytechnical Institute, and he will talk about initial steps in deploying and calibrating power system models on a Synchrophasor data cloud platform. Using, okay, there was something missing, I think, using FMI.
Yeah.
So welcome, Luigi.
Thank you very much, Christian. And it's very nice to virtually see some of you that I get to meet every 2 years in Europe for this very nice community. So this presentation is really on the initial steps that we're taking to be able to deploy models to the cloud. The work has been carried out by Giuseppe Laera and Marcelo de Castro, who are my PhD students at Rensselaer. And working with us is Chen, Wang, Chetan, Mishra, and Kevin Jones, who are in Dominion Energy. Okay. I'm trying to switch my slide, and I don't know what happened there. Okay. So the overview is described here. I'll tell you why we need to bring models to the cloud. Then I'll shortly just go over the background, and I'll tell you what we had to do to try to deploy this in the cloud platform where they needed to use. Before I start, on the right side of the screen, you have a Proctusian bell. So Proctus is, if you are not familiar with him, he was a rogue metalsmith from Attica in ancient Greece. So he physically attacked people by stretching them or cutting their legs to fit them in bed. And that's basically the meaning of this for us, is that Proctusian bed is an arbitrary standard which we are trying to exact conformity. Now, why is this in my presentation? Well, this is because of the needs for Dominion. So we cannot simply disregard phenomena that exist because it conflicts with the model. And in the power system world, the model is often the tool. So I'm going to show you what we found by actually just bringing the model into the cloud and starting to question it. So Dominion Energy is an American energy company. They operate more than 6,000 miles, American miles of transmission lines. They own power stations. The models that they use are mostly used for planning, some for operations, forensics, and to define control settings. But really, the challenge that in most cases to validate a model, it requires that an event happens in the grid. While the system is mostly on ambient conditions, so here you can see a spectrogram of 24 hours of data for one of the power plants that we're analyzing. And as you see here, around 10 hertz, you quickly see a mode or a frequency, an oscillation of the plant quickly decay and disappear. So, this was actually a 100 megawatt plant that was not monitored. And these problems cannot be really understood because of the model dynamics in the power system model that they use. So there is a new availability of this kind of data that was not before. However, it's difficult to be able to know what the model is producing versus what the data is telling, because models and data are completely segregated in most power utilities. So the vision of the project that we are now extending for 2 more years is to have cloud-based data-assisted modeling with Modelica-based technologies. And the idea is that we can access the Synchrophasor data, the measurements that originate this plot, within the predictive grid platform. This is a platform that allows access to all of the data that Dominion Energy has from the cloud. And it's basically built on top of AWS. Now, instead of building the entire power grid model in what we want to do is to basically create units for each of the power stations or even each of the generators so that we can actually modularly calibrate and do analysis for each of them. And this can actually help us do model validation and calibration on demand to support different tasks. Okay, so in this conference, maybe I should not talk too much about Modelica, but this is the core technology. What I tell people that most important things is that at least there are nine tools that support it natively. So in principle, you can move the models across tools. OpenIPSL is the library for power system modeling that I develop, well, not me, well, my team and other collaborators develop. And it's open source and it's high quality because we have verification against the reference tool that they use in the utility in North America and some Nordic countries, which is PSSC. So this is the tool that we use, and you can use it across several tools and generate FMUs. So here's a little picture of how a model of a tiny power system looks with the library. And this is if you wanted to do an interconnection study of, oh, we're going to install a new plant, you will assemble something like this that is some detail of the power plant generator, some of the controls that it uses. I'm not showing the turbine there. And a little bit of the power grid. And, I show people, well, the magic here is that you can even go down to the equations. Now, you cannot run Modelica explicitly on this cloud platform. There are certain requirements of how the provider, what they allow us to install or not. So that was the first constraint. Now, the next constraint was to develop this proof of concept was that all of the models for all of the generator units and all of the power plants are isolated in the simulation tool called PSSE. So they are basically limited to what that tool can do, and they cannot deploy that tool in the platform, primarily because it's a Windows application, but also it's not something that the software vendor allows them to do. So the solution was that, well, you can't really deploy anything, a standard Modelica tool. You cannot put your simulation tool there. So, I mean, we can create the models and deploy them with FMI. But the problem that we had is that the models for their specific power plants were not available in the library. So we have a little workflow here is that first, okay, implement the models from scratch and verify them that they comply with the accepted truth, which is this PSSC model for them. And then, if it works, we needed to deploy the models with source code and then integrate it with the predicted grid platform. So query data, pre-process the data, couple it with the FMU, and then integrate tools for model validation. And if this is successful, the process of calibrating and updating the model, then you could update parameters if the model is right, but nobody knows because they have not checked until you do this. So the software to software verification on the left-hand side, you have the diagram displayed by PSSC and the type of models. The parameters are not shown because this is it's not mine. It's critical information. But here you can see how the model is composed from these pieces that are in the library now. So a lot of these pieces, except probably one of them, have to be re-implemented and verified against PSSC. So here is some of the results on the tests that we conduct. We conduct a number of tests that you can see in this website that I'm deploying there. And here I'm showing the several variables and show how they match. PSSC is red, Modelon's impact is green, yellow, green, and diamola is on blue. So we get a perfect match to numerical precision, basically, of what we can offer. So having done that, we can export FMUs. But before that, we have to actually reconfigure the model. So if you recall, the model looks like that when we're verifying about against the power system tool. But now we actually have to play back measurements. So we have to choose which measurements to play back and which measurements to compare to. So what we do is that at the measurement location, which in this case is in the low voltage terminals of this generator unit, we are basically creating an interface block to which we feed the real and imaginary part of the voltage measured there. So this is basically where we're going to couple the measurements from the platform when it's deployed there. And this is the measurements that we're going to compare to the P out and Q out of the simulated model are going to be compared to those of the measurements. So that's how the two more important aspects. The rest is the simulation model. The other thing is that in simulation, we compute the steady state. Well, that doesn't exist in reality. There is no steady state. It's moving all the time. So what we do is that we try to calibrate, we try to find a value for the initial power dispatch and the initial voltage that would be used to that would be required during initialization. But now we have to actually fit it over time, actually, to be able to get a good comparison against the data. Okay, so the signal processing, we have some instruments called synchrophasors or PMUs that give us the measurements. So on the right-hand side of the screen, you can see how we query all the voltages and currents available from the specific unit. This is how we interface with that platform and select windows of data. And then we pre-process the data. So we basically do some filtering to remove some, basically some garbage and to narrow the frequency band that the model is able to capture anyway. So that's these two steps. The next step is to couple the model against those variables that I showed you before, which I'm skipping here because it's not so nice to show that. Now, the important thing is also to couple this to the optimization tool that is going to let us to calibrate the model. So we use from the Southern University of Denmark, they have a tool called ModSpy. So we could deploy anything that was in Python within that platform. So luckily, they have provided that tool, and we use that for the prototype. Then we need to instantiate the FMU. This is the station is WC. ST1 is a steam generator unit. That's why, and it's the first one. We define the inputs and output. Yep. Should move on.
12 minutes now. You should just go to the conclusion soon because then we could have also questions. Yeah.
Yeah. Okay. So basically, you know, we configure how the model should be run and calibrated, which parameters to calibrate over here, and the optimization settings. We run the optimization, and we get some result. The result is that our calibrated model is not matching so well yet, but you know, there is actually some additional dynamics that are modeled that shouldn't be there, perhaps. So you know, that's successful deployment, and we're getting close to the results. And the conclusions is that it's important to have open access, standard-based, portable, and reusable models using Modelica and FMI. This allows for model portability, and this gives benefits to the end user or owner of the models to be able to use the model somewhere else without specific tool dependency. So this is really fantastic. We showed that we could actually do this quickly for a cloud-based platform. We did everything with Python. And the new prototype actually allowed us to identify feature enhancements that that platform needs. For example, running optimization on those virtual machines is very inefficient. So they're going to have to size the virtual machines if you want to do optimization. And finally, this is a nice proof of concept. And we are now, this was a 1-year project. Now we're extending it for 2 more years and targeted specific plans to do in more detail. So we're going to enhance the prototype and try to implement some applications. So you saw the spectrum there. Our idea is that we should do parameter estimation optimization in the frequency domain where we have data all of the time and we don't have to wait for an event. Okay, sorry if I was talking too much. It's early in the morning here. I think I have time for one question.
Thank you very much. Yeah. Are there questions? Please raise your hands or write them in the chat or the Q&A. I would have a question. So what are your wishes towards the further development of the FMI standard? What are you missing? What is your experience?
I mean, I don't know if it's really the FMI standard or more the ability to actually use it efficiently, right? We did a lot of tests with FMI also before using ModSpy. I mean, I think it's more about the ability of end users like us to be able to understand and what is available there that you can do prototypes like this, and the material level of each of the things. It's a little bit unclear, right? So I mean, I have been doing this for a while with different projects, so it was not that hard, but it was hard to explain to other people why can we not do this or that. So here we had to use source code, which is, the licenses are not cheap when you have source code generation. So the only thing I could think about the standard is, and I don't know if that falls into the standard or not, is the cross-platform source FMU generation. Because we had to, one of the challenges that we had is that the utility cannot generate the FMUs themselves because they don't have Linux machines, but the cloud platform is in Linux, right? So for the new test, we're experimented with some cross-compilation features in one of the tools, but if there was a service where people could cross-compile for different operating systems, that would be useful. So that's the only thing that I could think that it's tangentially related to the standard.
Thank you. There's